Black holes are some of the most fascinating objects in the universe, about which we still know so little. These monsters have become the staple of science fiction flicks, which portray them as voracious monsters that swallow everything. However, for the first time ever, scientists have seen the inside of a black hole. What they have found inside is as scary as we've been made to believe. In this video, we join scientists as they dive in to finally see what is inside a black hole. There is something chilling about a black hole that implies nothingness, alluding to something that could draw us in and entrap us, a place where time has no meaning. With mind-boggling qualities that the same minds struggle to comprehend, what exactly is a black hole? What makes something that's essentially an invisible nothing so significant and powerful? The short answer is gravity and the pull of black holes. However, there is a longer answer that is even more fascinating. Black holes are created when small remnant cores of dead stars collide. If the resultant mass exceeds about 3 times the mass of the Sun, gravity overwhelms all other forces, causing the remnant to collapse and create a black hole. Black holes are extremely dense objects with so much mass that they have such a strong gravitational pull that even light becomes trapped. Most spiral and elliptical galaxies astronomers believe have black holes at their core. There are 3 different kinds of black holes. Stellar mass black holes are the smallest, weighing between 1 and 100 times the mass of the Sun. They form when the core of a large star collapses, resulting in a supernova or the explosion of a star. The most massive known supermassive black holes can have masses and millions, if not billions of times that of the Sun. It is believed that this type of black hole grows to its enormous size by merging with other black holes and absorbing stars. Intermediate mass black holes are a third category that, as the name implies, falls between the first 2. These ones are still a bit of a mystery, with only a few discovered, but each is thought to have a mass between 100 and 100,000 suns. These are thought to be the black holes that merge to form the supermassive variety. Not only do black holes explain the seemingly chaotic movements of some stars and contribute to our understanding of our galaxy, but they also represent a new realm of physics for scientists. According to Einstein's theory of general relativity, matter warps time and space, resulting in gravity. Black holes are extremely dense conglomerations of matter, hence their incredible gravitational pull. But from then on, they literally put Einstein's theory to the test. When we look at the singularity of a black hole, things quickly get complicated. The forces at work are so massive that science cannot agree on what will happen next. According to Einstein's general theory of relativity, when matter is drawn into a black hole, its information is destroyed. However, quantum mechanics says that this cannot happen. As a result, black holes provide a fantastic theoretical playground for astrophysicists and mathematicians attempting to reconcile the 2 theories. Black holes provide experts with a testing ground for fundamental theories that explain how the universe works, ranging from general relativity to quantum physics and string theory. There is a common misconception about black holes. People tend to visualize them as holes, but that is not true. A black hole can be compared to a supermagnet, except that instead of magnetism, which attracts metals, it has extreme gravity that attracts everything. Gravity is the reason we do not just float off into space every time we jump. The Earth's gravity is constantly pulling us towards its center, but it stops once we reach the surface. A black hole, on the other hand, has much stronger gravity than we do on Earth, and it doesn't have a surface to stop you. That is why it feels like you're falling into a hole, hence the name. Most people understand that a black hole is formed when a massive star collapses into itself and becomes extremely dense, a mass of an entire star compressed into a much smaller space. And because all mass produces some gravity, the more mass there is, the more gravity there is. This means that not only is the Earth attracting you, but you are attracting the Earth as well. However, the gravity of your body is much weaker than that of a planet due to differences in mass or weight. This explains why astronauts appear lighter on the Moon, which has less mass than Earth and therefore a weaker gravitational pull. It is still mind-boggling how compressed a black hole is. A star with the mass of our Sun may collapse into a black hole the size of a small city. That is extreme density. To put that into perspective, the Sun has a diameter of about 1.4 million kilometers, whereas a small city may only be about 10 kilometers long. Consider compressing the entire Eiffel Tower into the size of a single grain of rice. That is a significant reduction. As a result, calling them holes is only accurate in terms of what they do to their surroundings, not in terms of what they are. That quickly becomes extremely complicated. So if the black hole isn't a hole, what is it then? Technically, it is a sphere, a volume of space in the shape of a sphere. Black holes are made up of two parts, a singularity in the center and a hypothetical border known as the event horizon. The singularity in the center is a point with virtually infinite density that has no volume and is attracted to everything. This is the essence of black holes and the reason they have the properties they do. This point is theoretically infinitely small and dense. If you were standing on the North Pole, for example, the northern hemisphere would attract you more strongly than the southern, because gravity also varies with distance. This means that you are not experiencing all of Earth's gravity equally at any given time. The parts closest to you have more pull, while the parts further away have less pull. However, if all of this mass were contained in a much smaller volume, gravity would be more intense. This is because their masses are the same, and it is density that distinguishes a star from a black hole. Identity implies concentrated mass and thus concentrated gravity. The event horizon is what we imagine as a black hole in movies and illustrations, a dark circle in space. It is a perimeter around the center, also known as a point of no return. When crossed, it instantly pulls everything to the center. Even though the event horizon appears to be a border or edge, it is not solid and contains nothing. Keeping this in mind, black holes are not technically objects because they are mostly vacuums. The singularity itself contains all of the matter. The rest is just empty nothingness that appears black, as anything that enters falls to the center and merges with the singularity in a fraction of a second. Because black holes have such a strong gravitational pull that no light can escape, they cannot be seen directly. Instead of traditional telescopes, massive radio telescopes and gravitational wave detectors are used. Albert Einstein proposed in 1915 that when objects move through space, they create waves in space-time. This concept fuses space and time around them, so similar to how ripples move across the surface of a pond. In 2015, researchers at the Laser Interferometer Gravitational Wave Observatory, LIGO, observed gravitational waves for the first time, a century after their prediction. This was caused by the collision of two black holes 1.3 billion years ago. Black holes can be found by observing their effect on the environment, such as gas, dust, and stars being sucked in, becoming superheated and emitting radiation, which can be seen as a heat image. In April 2019, the Event Horizon Telescope, an array of 8 ground-based radio telescopes specifically designed to capture images of black holes, captured the first image of a black hole and its shadow in a galaxy called Messier 87, part of the Virgo galaxy cluster. The image depicts a bright ring surrounding a black hole 55 million light-years from Earth that is 6.5 billion times more massive than the Sun. This halo is a representation of the heat emitted by hot gas swirling around the event horizon, the very edge of the black hole as it draws everything in. When people hear of black holes, they wonder what goes on inside them. But what will happen if you fall inside? Whichever type of black hole you choose, the prognosis isn't great. Let's say you jump into a stellar mass black hole before anybody can stop you. Your body would undergo a process known as spaghettification, a funny name but a horrible reality. The gravity force of a black hole would compress you from head to toe while stretching you out, resulting in a spaghetti-like shape. A supermassive black hole has a slightly less horrifying effect. So imagine you choose one of these to make your great leap for humanity and scientific research, because there's no other reason to jump into a black hole. Sagittarius A** is a good candidate for this one-way exploration trip. It is a supermassive black hole located at the center of the Milky Way galaxy. Astronomers estimate its size to be 44 million kilometers in diameter and containing 4.31 million solar masses. Bruce Balick and Robert L. Brown discovered this black hole in 1974, but they didn't name it until 1982. Your journey into Sagittarius. A star truly begins after crossing the event horizon, which is the point of no return. You could see out from inside, but nobody could see you because any light would reflect back on you. The good news is that while the gravitational pull is much stronger than that of smaller black holes, the stretching tidal force is lower, so you won't be turned into spaghetti. However, the terrible news is that you wouldn't be able to escape. Or would you? Well, your only hope is the white hole theory. Simply put, if a black hole sucks things in, a white hole spits them out wherever that may be. Therefore, a white hole is an entirely different but related animal. Fortunately for you, the two are linked by an interdimensional tunnel known as a wormhole. So it is also possible that if you wait long enough, the black hole will turn into a white one. This process is expected to take billions of years, but don't be discouraged. Why? Because of the intense gravitational forces within, time would be accelerated for you, and it would be over in milliseconds. Of course, don't put your life on the line based on this theory, as scientists are still refining it. But let's get inside a black hole and see what happens there. Once you are trapped there, you could contribute to humanity's body of knowledge by carrying out a few experiments. It is possible that matter isn't squished down to an infinitely small point deep inside a black hole. Instead, the smallest possible configuration of matter, the smallest possible pocket of volume could exist. A Planck star is a theoretical possibility envisioned by loop quantum gravity, which is itself a highly speculative proposal for creating a quantum version of gravity. In the world of loop quantum gravity, space and time are quantized, and the universe around us is made up of tiny discrete chunks, but at such an incredibly small scale that our movement appears smooth and continuous. This theoretical chunkiness of space-time has two advantages. One, it brings quantum mechanics' dream to its logical conclusion by explaining gravity in a natural way. Second, it prevents singularities from forming inside black holes. Matter encounters resistance as it squishes down under the immense gravitational weight of a collapsing star. The discreteness of space-time prevents matter from traveling any further than the Planck length, approximately 1.68 times 10 to the power of minus 35 meters. Everything that has ever fallen into the black hole is compressed into a ball and no larger than this, perfectly microscopic, but not infinitely small. Because of this resistance to further compression, the material eventually uncollapses, a not so violent term as explodes, rendering black holes only temporary objects. However, due to the extreme time dilation effects around black holes, it takes billions if not trillions of years for them to go boom from our perspective in the outside universe. The Gravistar is another attempt to eliminate the singularity that doesn't rely on untested theories of quantum gravity. The name may seem like a jumble of parts thrown together in the backyard. The difference between a black hole and a gravistar is that the latter is filled with dark energy rather than a singularity. Dark energy is a substance that pervades space and time, causing it to expand outward. Dark energy is currently at work in the universe, causing our universe's expansion to accelerate. When matter falls onto a gravistar, it's unable to penetrate the event horizon due to all the dark energy on the inside and thus remains on the surface. Gravistars, on the other hand, appear and behave like ordinary black holes. Remember that the event horizon of a black hole is its point of no return, the boundary beyond which nothing, not even light, can escape. Recent observations of merging black holes by gravitational wave detectors such as LIGO and Virgo have potentially ruled out the existence of gravistars, because merging gravistars will give a different signal than merging black holes. Gravistars aren't exactly forbidden in our universe, but they are on shaky ground. Now, Planck stars and gravistars have fantastic names, but they're not the only theories out there. Scientists have proposed a more realistic explanation for the existence of black hole singularities, which is derived from a better understanding of the characteristics of real black holes. Rather than being based on the stationary, non-rotating, uncharged black holes that we typically imagine, real black holes are far more complex, with varying personalities that depend on their spin. A rotating black hole, for example, stretches the singularity into a ring which, according to Einstein's general theory of relativity, allows you to enter a wormhole and emerge through a white hole into a new patch of the universe once you pass through the ring singularity. However, rotating black holes are also extremely unstable, and this is where things get complicated. The singularity ring rotates at such an incredible speed that it generates an enormous centrifugal force that acts like anti-gravity. This results in the formation of an inner horizon within the black hole, where radiation falls inward towards the singularity from outside the region, propelled by the extreme gravitational pull. However, radiation is pushed away by anti-gravity near the ring singularity, with the inner horizon serving as a tipping point. If you reach the inner horizon, you would encounter a wall of infinitely energetic radiation, with the entire history of the universe blasted into your face in less than a blink of an eye. This phenomenon ultimately sows the seeds for the black hole to evaporate. Although rotating black holes exist in our universe, our current understanding of math suggests that the formation of an inner horizon within these black holes is incorrect, and something peculiar is going on. Nevertheless, thanks to the concept of gravitational waves, we have been granted our first glimpse of what is happening inside black holes. Scientists have proposed a more realistic explanation for the existence of black hole singularities. which is derived from a better understanding of the characteristics of real black holes, rather than being based on the stationary, non-rotating, uncharged black holes that we typically imagine. Real black holes are far more complex, with varying personalities that depend on their spin. A rotating black hole, for example, stretches the singularity into a ring, which, according to Einstein's general theory of relativity, allows you to enter a wormhole and emerge through a white hole into a new patch of the universe once you pass through the ring singularity. However, rotating black holes are also extremely unstable, and this is where things get complicated. The singularity ring rotates at such an incredible speed that it generates an enormous centrifugal force that acts like anti-gravity. This results in the formation of an inner horizon within the black hole, where radiation falls inward towards the singularity from outside the region, propelled by the extreme gravitational pull. However, radiation is pushed away by anti-gravity near the ring singularity, with the inner horizon serving as a tipping point. If you reach the inner horizon, you would encounter a wall of infinitely energetic radiation, with the entire history of the universe blasted into your face in less than a blink of an eye. This phenomenon ultimately sows the seeds for the black hole to evaporate. Although rotating black holes exist in our universe, our current understanding of math suggests that the formation of an inner horizon within these black holes is incorrect, and something peculiar is going on. Nevertheless, thanks to the concept of gravitational waves, we have been granted our first glimpse of what is happening inside black holes. The new work may eventually aid us in understanding what happens when black holes merge, which is possibly the most dramatic and extreme event known in the universe. In 2015, gravitational waves were discovered for the first time. Scientists used massive and precise equipment to observe the wobbles in space-time that occur when black holes collide, causing disruptions that reverberate throughout the universe. Since then, scientists have detected nearly 100 emerging black holes via gravitational waves that have spread throughout the universe. Scientists compare the process to shaking a box and trying to figure out what's inside by listening to the sound that comes out. In this case, the shaking is caused by the collision of two black holes, and the sound is caused by the study of the gravitational waves they emit. These measurements were used in the new study to improve models of cosmic events. Scientists should be able to map the structure of what is going on inside and test how Einstein's theory of general relativity holds up in extreme environments. As a result, until recently, scientific models relied on linear interactions, which worked well but had limitations because they did not account for other types of behavior. New research on non-linear interactions could improve models by up to 10%. It will also help scientists detect more colliding black holes in the future. It is a significant step toward preparing us for the next phase of gravitational wave detection, which will deepen our understanding of gravity and these incredible phenomena occurring in the far reaches of the cosmos. Thanks to the pandemic, the LIGO Observatory, which first detected gravitational waves, has been offline since 2020. However, new systems will be activated in the coming years that may detect more black holes in greater detail. Black holes are among the most enigmatic phenomena in the universe, but a new study from the University of Michigan has added to the mystery surrounding these deep space wonders, claiming that black holes are simply holograms. In all fairness, these researchers aren't claiming that black holes are holograms in the way that most people think of holograms, as some kind of sci-fi projection. Instead, they're experimenting with holograms to see how the inside of a black hole connects to the outside. The research led by Enrico Rinaldi is based on the concept of holographic duality. This states that the theories of gravity and particles are mathematically equivalent. The theory of gravity describes the third dimension, whereas particle theory describes the second. In terms of black holes, both of these theories are relevant in describing how they function. The study investigated what this holographic duality concept means for black holes and what lies within them. Our understanding of the inside of a black hole is heavily based on a gravity theory, which suggests that it operates in the third dimension. From the outside, space-time flows into and through a black hole. The outside of a black hole, however, is not calculated in the same way as the inside. This is despite the fact that the inside of a black hole operates in 3 dimensions, whereas the outside is perceived as flat. Ronaldo's latest research utilizes 2 simulation methods simultaneously to calculate and describe the gravity of a black hole. Inside a black hole, the gravitational pull is so strong that it is impossible to observe with our human eyes. Instead, a mathematical model must be calculated. Ronaldo suggests that the way we perceive what is happening inside a black hole is best described by a holographic projection. In this case, a hologram is a flat or 2D image that displays a 3D image. Researchers have described a black hole with a 3D center that is projected to us through particles calculated in 2 dimensions using quantum matrix models. These latest calculations show that the inside of a black hole can only be described mathematically. We won't know if what we see in 2D, 3D, or beyond is all there is until we can perceive the inside of a black hole in a way that contradicts our current understanding of the nature of the universe. The sight of a black hole swallowing objects is a sight to behold. Recently, a previously unknown black hole announced its presence to astronomers when it ripped apart and devoured a star that got too close. The star was shredded by an intermediate mass black hole in a dwarf galaxy a million light-years away in what astronomers call a tidal disruption event, TDE. The TDE became visible when it emitted a powerful radiation flare that briefly outshone every star in its dwarf galaxy home. This TDE may aid scientists in better understanding the relationship between galaxies and the black holes that reside within them. It also gives astronomers another intermediate black hole to investigate. This discovery sparked widespread interest because it allowed scientists to not only find more intermediate mass black holes in quiet dwarf galaxies, but also measure their masses. The TDE flare, known as at 2020 NEH, was discovered by astronomers using the Young Supernova Experiment, YSE, an astronomical survey that detects short-lived cosmic events, such as supernova explosions. As the black hole begins to devour this star, the observation of this initial moment of destruction was critical in allowing an international team led by UCSC scientists and Niels Bohr Institute astronomer Charlotte Angus to measure the mass of the black hole, which was found to be between 100,000 and 1 million times the mass of our Sun. TDEs have previously been used to successfully measure the massive supermassive black holes, but this is the first time they've been demonstrated to work in documenting the masses of smaller, mid-sized intermediate mass black holes. That means the initial sighting of the incredibly fast at 2020 NEH flare could serve as a baseline for future measurements of mid-sized black hole masses. Physicists have long suspected that supermassive black holes, which can have masses millions if not billions of times that of the Sun, could form as a result of the merger of intermediate mass black holes. According to one theory, the early universe was rich in dwarf galaxies with intermediate black holes, which could have facilitated this growth. As these dwarf galaxies merged or were swallowed by larger galaxies, their intermediate black holes cannibalized each other, increasing in mass. This chain reaction of ever larger mergers would eventually result in a supermassive black hole that sits at the center of most galaxies. One unanswered question about this theory of black hole growth is whether all dwarf galaxies have their own intermediate mass black hole. Because black holes trap light behind an outer boundary known as the event horizon, they're effectively invisible unless they're feeding on surrounding gas and dust or ripping up stars in TDEs. Tell us what impressed you the most in the comments below. And make sure to subscribe to Unknown Realms of Technology for more exciting videos.